Hi students, in this class we are going to see very important topic, thermodynamics. Thermodynamics, the name itself comes from thermos plus dynamics. Thermo means heat and the dynamics means movement. So movement of heat when it is in a equilibrium position. So we are going to discuss few important concepts. Open system. In the open system, energy and matter both will exchange. There is one thing called system and surroundings. We might have learned these things, basic introduction. System is the part which we are interested about. Surrounding is apart from the system, everything else is called surrounding. Closed open system is both mass and energy are exchanged. In a closed system, only energy is exchanged, not the mass. And isolated system is like neither mass nor the energy. Open system example we can give, just like you are boiling heat. Strong statement. You are boiling water open to the atmosphere. Now here our system is container. A little larger. In a container you are heating water. Okay. Now when you are giving heat, the heat is exchanged with the surroundings. What is the system? Only water is our system. Apart from the water, everything else is called surrounding. When we are giving heat, it is exchanging mass. So some water is getting evaporated and it's getting heat also. Energy is exchanged. Closed system is only energy. Now just cover it up. Cover the container. So it will be like only heat is given and mass is not coming out of the system. Isolated system is just don't give any energy and just like a thermoflask. No heat. If you keep water for some time, hot water, it remains as it is. Okay, this is like isolated system. No energy, not the neither energy nor the mass. There are actually thermodynamics basically deals with the equilibrium positions. Equilibrium means there are three basic equilibriums. Mechanical equilibrium, net force is equal to 0. Whenever you see question anything regarding the thermodynamics, you should assume the net force is equal to 0. Unless net force is equal to 0, that is not even said to be in thermodynamic equilibrium. Thermal equilibrium, so there will be no temperature gradient. See, uniform temperature in all parts. See, there is like if I am heating the gas, it's not be one side one temperature T1, another side temperature T2. It will not be like that. Temperature will be uniform throughout the system. And chemical equilibrium, if you see for equilibrium we will use Gibbs free energy. If you remember the chemistry part, Gibbs free energy, and there is something called diffusion. So there is called composition, mostly we say chemical composition throughout the system. And first law of thermodynamics. Before discussing about first law of thermodynamics, we should know one thing called internal energy. Internal energy. Sir, what is the meaning of internal energy? Take a system. In that, say it is a gas, supply heat. When we supply heat, the temperature rises. That can be externally measured, the temperature change. If you see internal molecular arrangement, internally molecules start moving randomly with a more high velocity compared to if we don't give heat. So in this case, when we give heat energy, some property of the gas or water or any liquid is changing. So kinetic energy, internal molecules kinetic energy is increasing. But can we measure it? So one atom goes in the other direction, another goes in another direction. Because of movement of these molecules or atoms, the rise in temperature occurs. This is called internal energy. Internal energy is basically internal property. Okay, I will give one simple example. I am giving 50 joules of heat. Okay, and the system performed, water did 40 joules of work. Water did 40 joules of work. What about remaining form of remaining? So it did how much? 40. I gave 50 rupees to you, you performed, you just spent 40 rupees. What about remaining 10 rupees? Remaining 10 rupees are with you only, but it's you are hiding it. So similarly, the internal energy is a property which is hiding in a material, which cannot be measured with any instrument. And one more thing, internal energy is a state function. State function, so it doesn't depend on path. Okay, it doesn't depend on path. And we have formula for internal energy also. We denote internal energy with delta U. Delta U is equal to mCV into delta T. Okay, this is heat capacity. Yeah, CV is a, I will explain more elaborately in the next part. So delta U is equal to, okay, mCV delta T, it is also NCV into delta T. M is mass, N is moles, depend on specific and molar, the specific heat capacity and molar heat capacity, so molar cases. Okay, this is internal energy. Energy units are joules. And there is one more thing, work. Okay, work. What is a work? Work is nothing but force into displacement. dW is equal to force into displacement. Force is nothing but pressure into area. Force is nothing but pressure into area into dx. A dx is nothing but small volume, integral P dV. So the work done, I'm sorry, I did a blunder. So here it should not be dW, W is equal to, and yeah, W is equal to integral F dV. So W is equal to integral P dV. Then we are going to explain about this work done is state function or path function. It is a path function. It's a path function. Now we are going to see derive first law of thermodynamics. Okay, so listen carefully. Say I am giving, so I am going to give Q joules of heat, Q joules of energy to gas. What can happen? It can perform work and it can change in internal energy, also can change. I want to remind you one more thing. Absolute value of internal energy, cannot be measured. Absolute values at particular position. So thermodynamics basically deals with three things: pressure, volume, temperature. These are called state function. If you are able to represent a system in pressure, volume and temperature, that is called thermodynamic representation. Okay, so when I give Q amount of heat, it can do some amount of work. There can be some increase in internal energy if there are no other losses. He is going to say, according to the first law of thermodynamics, some amount of heat dQ is equal to du, or change in internal energy, plus dW. dQ is equal to du plus dW. What is du? Ju is the internal energy because of random movement of molecules, and dW is a work done. Okay, so Q. Now we are going to see very important point, sign convention. Amount of heat, if Q added to the system, then Q becomes positive. If Q heat is removed from system, then it is negative. Work done by the gas, work done by the system is positive. work done by, see, when I was teaching in the class I said negative, but I changed the formula here. So depends on the formula, work done by the gas system surroundings changes. Okay, work done by the system is positive in this case because we are using this formula. Work done on the system is negative. Okay, work done on the system is negative. Okay, internal energy, if the raise in temperature, okay, that I will explain in the next parts. So sign convention is done. Let's go to the specific heat of gases. What is the specific heat of gas? If you remember, specific heat is equal to there are two types of specific heats. One is at constant pressure and another is at constant volume. Constant pressure and at constant volume. Okay, let's derive at constant pressure. At constant pressure, it will be specific heats. Understand, specific means we include mass. Molar, it's not molar specific heat. So specific heat at constant pressure, Cp is equal to 1 by m into dq by dt. dq by dt. Cp is equal to, this is at a constant pressure. If I want to know dq, dq is equal to m into Cp into dt. Okay, so if Cp is not function of temperature, which is nothing but if Cp is constant, Q is equal to amount of heat given. Q is nothing, delta Q is equal to mCp into delta T. Delta Q is equal to mCp into delta T. Next, delta Q over, next, if it is not, Cp is function of temperature. If Cp is function of temperature, so dq will be delta Q is equal to m, we can take out common, integral Cp into dt. Limits are varying from T1 to T2 depending on the temperature levels. So molar at constant pressure we are done. What about constant volume? Remember, these are all specific. Specific means we should include mass. And here constant volume, next we are going to see. If constant volume, Cv is equal to 1 by m dq by dt at constant volume. So delta Q is equal to mCv into delta T if Cv is constant. Constant means it is not, Cv is not a function of temperature. If Cv is a function of temperature, delta Q is equal to m into integral Cv dt. Okay, Q at constant volume, understand, this is not at a constant pressure. Next, molar specific heats. Molar specific heats, Cp at constant pressure is equal to 1 by n dq by dt at constant pressure. Here n is number of moles where m is a mass. Here is m is a mass. Moles, and Q is equal to, delta Q is equal to n Cp into dt if Cp is not function, and Cv is equal to, and I am writing the same thing, delta Q at constant pressure, delta Q at volume is equal to n Cv into delta T at if Cv is constant, right, and Cp is constant. If it is variable, it is n into integral Cp into dt. It is n into integral Cv into dt. N is number of moles so constant. And yeah, one more important thing, the ratio of, okay, let's see about units of specific heat. Units of specific heat is, I'm sorry, some student commented. Okay, wait a minute. units of specific heat. Okay, N is equal to, what is our joules per mole Kelvin? Joules per mole Kelvin. These are the, so if you want, how we got joule by N into delta T. This is nothing but Cp or Cv. Whatever value, the units will be same, joule per mole Kelvin. Okay, let's go to some important definitions. Cp by Cv, if you know thermodynamical property gamma, these are all molar specific properties. You should not include this m term. You should include, when you are writing Cp by Cv is equal to gamma for both the cases, and Cp minus Cv is equal to R in this case especially. Okay, molar Cp and Cv are molar specific properties. Okay, molar specific heats. And then if we substitute this, Cp minus Cv is equal to, and we can get the value of, okay, so substitute Cp is equal to, see, gamma Cv into gamma minus 1 is equal to R. So Cv is equal to R by gamma minus 1, and Cp is equal to, then what is the value of Cp? Cp is equal to gamma into, substitute in the first expression, gamma into Cv, gamma into R by gamma minus 1. This is the value of Cp. Okay, next, so there is something called degrees of freedom. Degrees of freedom. Degrees of freedom, if you remember, degrees of freedom, there is a relation for gamma and degrees of freedom also. And gamma is equal to 1 plus 2 by F, 2 over F, where F is degree of freedom. Okay, if you want to extend this, gamma is equal to, so let's write Cp. What will be the value of Cv is equal to, Cv is equal to F by 2 into R. Cv is equal to F by 2 into R. Then Cp is equal to, if we substitute the values, and it is equal to 1 plus F by 2. If I substitute properly, let's see once again, gamma, so it will be gamma 1 plus 2 by F by, so 1 plus 2 by F minus 1, it is into R. So Cp is equal to 1 plus F by 2. So because 1 gets cancelled, and if it goes to our numerator, 2 by F gets cancelled, 1 plus F by 2 into R. This is the value of Cp. Cp and Cv values are we got. Next, there are monoatomic and diatomic gases. First one, so atomicity or monoatomic. Monoatomic, what will be the value of gamma, F is equal to how much for monoatomic? Degrees of freedom is 3. If degrees of freedom is 3, then Cv value is equal to, you can substitute here 3 by 2 into R, then Cp is equal to, so 1 plus, so 5 R by 2. We can get the value of gamma then. Next, second, diatomic. Degrees of freedom is, in this case, degrees of freedom will be, so how it will be 5 types, the monoatomic gas. So it is equal to 5 degrees of freedom. How, sir? Diatomic. So if they are placed like this, how each body, how many ways you can move? 1, 2, 3, and 1, 2, 3. So 3 plus 3, but they are confined with 1. 6 minus 1, 5. So if I explain this in the class, but remember this part, and you studied in the chemistry part, diatomic is 5, Cv is equal to 5r by 2 and Cp is equal to 7r by 2. Third one, triatomic. Triatomic degrees of freedom. See how this triatomic, there are two types, non-linear and linear. If there is a linear one, so there will be like 7 degrees of freedom. 7 degrees of freedom. So 1, 2, 3. So these three are, if you see here properly, 3, 3 and 3 degrees of freedom. 1 minus 1 minus 1. So 9 minus 2. So total 7 degrees of freedom. So most, if you are new student, you cannot understand this why I am writing 7 degrees of freedom, and Cv is equal to 7r by 2 and Cp is equal to 9r by 2. So fourth one, triatomic non-linear. Triatomic non-linear is, it has degrees of freedom of 6. It has 6 degrees of freedom, non-linear, and because see, if there are atoms are like this and 1, it has 3 degrees of 3 ways it can move, and it can move 3 ways, it can also move 3 ways, but these two are confined to move in one direction, 1. These two are confined to move in only one direction, 1. These two are confined to move in one direction, 1. Total only constraints 3. So 9 minus 3, 6 constraints are, so 6 degrees of freedom it has, and 6, and Cv is equal to 3r, Cp is equal to, and it is equal to 4, 4r. So this is these are the most important properties to be learned. Thank you.